Okay, guys, welcome. I can see people are logging on now. I just keep having massive panic attacks because I'm not very good at this Zoom, trying to get everything working, but hopefully you can hear me and that you can see my screen. It's good. We've got 24 logged on, going up nicely. The Q&A thing doesn't seem to be working, but we don't have anybody after us until 1 o'clock. So what I'll do is try and figure out, if you have got a question, hang on at the end, type it in, and I will be able to look at those at the end and go through any that we've got. It might be that I have to take off screen sharing for that to work. So we'll bear with me on it. As I say, I'm really out of my comfort zone with these. Right, okay, so we've got about 30 people here. I am recording this today, so I'll get started and see where we go. So this is the triple only content, and it's a few bits and bobs, but broadly, if you've looked at the slides, it's around sound waves and then a little bit on seismic waves at the end. So we first of all will consider how the key language that we're going to be using when we talk about how a wave interacts with a material. So if a wave passes straight through, the language that we have to use is transmission. We're familiar with reflection and refraction when it moves to a more dense material that causes it to slow down and refract towards the normal. Diffraction is where a wave passes through a small gap and then spreads out on the other side. There might be an absorption, and if there is an increase in internal energy of the object, and one that is highly unlikely to come up, which is called scattering. Okay, which is essentially, that's your ripple in your pond that you'll see if you put a stone in the center and you've got a ripple coming out from around there. A couple of other things that's triple only, so I didn't include it when we did the reflection stuff last week, is the different types of reflection. So we did this one here where we've got the angle of incidence equals the angle of reflection with the normal coming down and the reflective surface, typically a mirror. But this is the simple version with just one beam of light coming down and one being reflected. Naturally, you know that there are multiple beams of light coming, oops, sorry, too sensitive, multiple beams of light coming down and multiple that will be reflected, and that's called specular reflection. So if you had to complete a diagram of this, that is what that would look like. Now here we've got a reflective surface, but you can see that it's bumpy. So this is called diffuse reflection, and you'd get this, I guess, if we were in a lab, for example, and I wanted to demonstrate this, it might be some tinfoil that has been slightly scrunched up, and it's still reflective, but it doesn't obey, well, it does obey the law of incident ray and reflected ray, but because they're all at different angles, it would appear that it's chaos, but there isn't. You can see that everything would still be, the normal would just be perpendicular to that surface at that time. So whereas here it's coming down because the surface is flat, here we can see a curved edge, so the normal would be perpendicular to that surface, but if we look at it as a whole, it just looks like a big mess. It's called diffuse reflection, and when the surface is bumpy. Specular reflection, which is basically a more advanced version of the mirror reflection. Next week's webinar will be on lenses, and we're bringing stuff back from biology on that, and so we'll be looking more at this sort of stuff when we do lenses next week. Going back to essentially the sound wave stuff and how they behave, I remember teaching this to some of you in Key Stage 3, and hopefully you're looking at this thinking, yeah, this does seem familiar. So we talk about the sound wave oscillation, or the vibration of the sound wave, being parallel to the direction of the wave itself, or the energy that's transferred. So we have here the sound wave that is coming in to the ear canal at this point. What happens, and you have to sort of be able to describe this, is that this sound wave causes the eardrum to vibrate. They in turn called the 3 smallest bones in the human body, the malleus, the incus and the stapes, or the hammer, anvil and stirrup for their common names. Together they're called the ossicles. They then in turn vibrate together and cause the fluid inside the cochlea. Inside the cochlea there's a load of fluid, and inside these here, which are called semicircular canals, that causes movement of this fluid. Some of you will be aware that this is where our sense of balance is also controlled. Now inside these cochlea here, there are these tiny microscopic hairs, and it's the movement of those hairs that stimulate the auditory nerve. Okay, and so that then jumps from being a mechanical movement to an electric impulse that travels up an auditory nerve, and how it feeds into your understanding of biology in that way. So let's just go through this again for the avoidance of doubt. The oscillations or vibrations are parallel to the direction of transfer, energy transfer, and the vibration hits the eardrum here, causing that to vibrate in much way that a drum itself vibrates. Then you've got the 3 ossicles that transfer this vibration through, and then when it hits the cochlea, you've got the liquid in the semicircular canals and these tiny little micro hairs that sit on the cochlea that also vibrate and then are sent through to the auditory nerve. Interestingly, not part of physics, your physics GCSE, but I thought, you know, let's link it back to the biology. Hearing with a cochlear implant is where you have, and you'll see people who've got a cochlear implant, they'll have something attached here about this point here onto their skull, and then on the inside, the implant, which is actually magnetic, attaches on the other side, and the electrode directly stimulates the auditory nerve. So that's how people who can be profoundly deaf, they have a problem generally with their cochlea, and those little micro hairs don't work or don't function properly. They can still, a microphone picks up the sound vibrations here, and then it all travels down through there like that. Hearing loss is most commonly associated with the damage of these little hairs here. Okay, and so that will then not stimulate the auditory nerve, and those little hairs are mainly damaged by overuse. So listening to particularly loud sounds, for example, causes deafness because of these little hairs that have been damaged. And once they're damaged, that's then gone. You don't regrow them. That's not one of the nerves that regrows, or the cells that can regrow in us. So. Just to remind ourselves, the speed of sound in air is approximately 330 meters per second. Because it's the movement is the vibration of particles, in air the particles are more spread out. So this is the slowest speed, which always might seem a little bit strange, because you think, well, how can sound travel through a solid more quickly? But the particles are closer together, so they're vibrating more. Okay. But if we go back to our understanding, it might be that actually we want them to transmit through, but maybe they become absorbed as they're going through. They lose the energy, and so they become more absorbed in that way. So we'll just move on now to talk about ultrasound. Quite straightforward, really. It's the human hearing range that is above. Our human hearing range is 20 hertz to 20,000 hertz, and ultrasound is any hearing or frequency above 20,000 hertz. So animals like your dolphins and dogs, and they can hear in ultrasound, and that's anything above that would go from there. And we'll look at what we use ultrasound for next. So human hearing range is 20 hertz to 20,000 hertz. If you think about it, it's a bit crazy. The cochlear hairs within our cochlea vibrate between 20 and 20,000 times a second to stimulate that auditory nerve. So they're quite big numbers, really, if we actually sort of get back to the nuts and bolts of it. The conversion, as we've talked about, works over limited frequency in the structures that we have in the ear. So that's why we can only hear up to 20,000, and other animals with different structures can hear differently as well. So I've tried to sort of link this back into things that we've done previously. So we can have a look at these ultrasound here. I'm hoping you'll recognise this as an ultrasound of a fetus, looking probably at the 20-week scan, perhaps something more than that. And you can clearly see the bones of the spine coming down through here. And we can see here where the skull is, and in point of fact here, where the babies, when they're first born, have that soft bit at the top of their head where the skull hasn't fully formed yet. And you can see that that's happening there quite early. So actually this could be sort of a gestation of beyond 20 weeks, to be perfectly honest, from there. So that is and then where we don't see anything, that's the amniotic fluid. But here we use ultrasound not just for abnormalities in fetuses, and so we have done a dissection of the kidney. And when we did that, whilst we didn't see in probably, you know, just about made out, didn't we, these medullary pyramids, and then we have around the outside this cortex, and we noticed that they were made of a different tissue. And that gets picked up in the ultrasound. So ultrasounds can be used, you see, to spot abnormalities in that way. If there was a growth there, then they could see that tumour quite easily. They also do ultrasounds of the heart and many organs within the body, because it's safe. It's a sound wave. It's not a ultra. It's not a X-ray, it's not the electromagnetic spectrum, of which we're going to talk about on tomorrow, but it's a much safer way to do this. So there's less energy, essentially, that is, they're not ionizing these rays that come through. They're not causing damage to the individual tissue from there. And what happens is it's a reflection, and so these are attached to like a receiver, and there is a reflection that comes back, and then that can be made into a picture from there. What you will have on each of these is like a conducting liquid that will allow the ultrasound wave to pass through the liquid and into the body more easily, so they can get a better resolution of image in that way. Bats, as we're aware, use echolocation to find their prey and avoid things. Here, so that's an example of the ultrasound waves, the high frequency waves that are being emitted from the bat, and they use that to, the reflections that come back are very accurate in how a bat perceives the world around it. As you are aware, they have very poor eyesight. And so this ultrasound from the bat has then been taken. Many things come from the natural world. The ideas come from the natural world. And this is here and here as well. So we can see ships using sonar to be able to determine, warships would determine the nature of submarines, for example, and here we are doing the bottom of the seabed and looking at what's down there, the depth, and also the nature of it. So those companies that explore for, they call them hydrocarbons, but we know it as basically gas underneath the surface. Those things are used and made up using the sonar and things like that as well. You would have to work out depths of things using the speed equals distance over time. Okay, so they would give you some information and you'd have to work out how deep something was. You may have to work out the speed of something, you know, rearrange the equation, but normally it's about working out the depth. So if we look at this here, just look at this information, if we're saying we've got this picture and sound travels at approximately 1500 meters per second in water, so you can see that is much faster than it is in air with the 330. It takes 8 seconds to send and receive the signal, so you'd have to halve that, 4 seconds down, 4 seconds back. We could work out the depth of 1500 times 4 equals 6000 meters, for example, in this one. This is a very common little bit of maths to be put in with the work on waves that is different from the wave equation. Those are the two, they're the main two, to be honest, with your maths in terms of calculations that will come up. So we've got working out the depths of things and also finding defects. So you would here we can see if there is a reflection back, it means that there is there's a defect in this as well. And on the next slide, or one of the exam questions at the end, we can look at that in a little bit more detail. So that's just the remind yourself of the human hearing, and then anything above that is the ultrasound. Yeah, I think that's pretty much everything that we've covered on ultrasound, that it's the frequency above and various uses of it, how it works. So they're either absorbed or it's reflected, come back in using these bits here, whether it passes through, whether it's absorbed or whether it's reflected through. Next, we're going to look at seismic waves. Now, I forgot, I was going to look at the geography curriculum actually, because some of this you may be familiar with already. P and S waves. I was sort of, before I looked at this, well, P and S, primary or secondary, which now makes more sense. The primary wave, the first wave, is longitudinal, and its oscillations, as we know, are parallel to the direction of the wave, and they travel, so it's like sound waves, and they travel at different mediums depending, travel through all mediums but at different speeds depending on the medium that it is in. These ones are very destructive. The secondary wave, or the S wave, is the transverse wave, and we now know that these oscillations are perpendicular and they are slower. Also, they cannot travel through liquids. I'm talking here about seismic waves. Please don't just now say anything about transverse, no liquids. Okay, we are talking about seismic waves that are prevented from traveling through the outer core here. Okay, so when an earthquake is happening around the globe, scientists have installed these seismometers around our Earth. They detect they're around to detect earthquakes, and what they have to do is they normally triangulate. They normally have 3 different readings that they would need to be able to do to work out where the earthquake, the original point of the earthquake was. And they use that by working out the time it takes to receive something, and they know sort of like the speed of something through the rock, through the crust at this point here. So if they know the time that it takes for something to travel, then they can work out, you know, the distances that they can pinpoint that into the epicenter there. So there's that understanding of seismic waves. But also there's this phenomenon that because these S waves do not travel through the outer core, they have led to our current understanding of the Earth. You see that there is something that's molten here in the center, and we've got huge refractions here, as we can see when a wave, a P wave, has hit the outer core and has been violently refracted, and then comes back out. This refraction here as well, and comes out here. So this is how we've come to our understanding of that. Coming through. I can see we've got some questions popping up on here, so we'll have a look at that in a bit. How are we doing for time? Good, 20 past. So what might that look like in terms of the exam questions, because half an hour of the exam is going to be triple only content. And we've got here spotting the faults. So diagram shows a high frequency wave can be used to check for internal cracks. How does it show this? What happens here and here? This is where the pulse is transmitted. At this point here is the crack, because we can see there is a reflection come back, okay? And here we can see at that point as well. That's the end point of the bolt, and that comes back to the end here. So here's the bolt end here, but mostly there is a large crack in here because it has been it's been reflected back at that point. There is a gap, you know, it gets to the end and then, you know, hits something and then comes back. Here we go. Use the information in the diagram and the equation in the box to calculate the distance. So it always gives you, you're not expected to know any of these speeds unless you've got obviously the distance and the time, and then you might have to work it out. So here then we're looking at a scale of 1 centimetre to that value here. So we'd work out how far that is in terms of the time that it's taken. So we do the speed times the time equals the distance from that. Here is one which I thought was quite unusual. Pigs have a layer of fat in their skin. Underneath the fat is a layer of muscle. So we're looking at two different tissue types. Ultrasonic waves are used to measure the thickness of the layer of fat. An ultrasound transmitter and detector are attached to the skin of the pig. Explain why ultrasound can be used to measure the thickness. So we're talking here, aren't we, about how we've got the ultrasound wave can pass through the skin of the animal, but it will be reflected at the next layer of muscle. So we'll be able to determine that difference between them. But it doesn't matter the distance, measure the distance, it measures the time it took. Yeah, and then we also need what's the conductive value of that? What's the speed? How long does it take the average ultrasound wave to pass through the layer of fat in a pig? Okay, because without that we cannot put it into these equations here. So anything that you have around this is about your knowledge. Your only knowledge is that you need to know the distance equals speed times time equation, and you need to think about all the information that you've been given. How does that fit into this? And my understanding that the ultrasound can pass through some things but not others. Okay, and in being able to do that, these kind of questions, they are level 3 questions. You won't get them, you know, particularly more difficult than this. And I did try to choose some that were a bit like, ooh, weird. Then that's what your thinking behind it has to be able to answer those sorts of questions, which some of you do very well already, but some of us, that's an emerging skill for us, I think. Okay. So last of all then, on these little slides, there's a little poll, which we'll just go through quite quickly. And then I'm going to want to leave a little bit of time. We've been quite limited. We're not allowed to talk for too long. I will try and answer some of these Q&A questions. Okay, so let's go with these poll. Poll number 1 is, let's launch that for you so everybody can see it, not just me. Normal hearing range, what can we remember as that being? What is normal hearing range? Oh, this is looking encouraging, can tell you all triple science students. Okay, I'll call it a day there. Everybody who voted got it right, between 20 and 20,000. We've got poll 2. Let's have a little look at that. Yes, what are the collective of the small bones? The collective of them. There's 3 of them. What are they called? Okay, about the same number of people who voted, so I'll end the poll and share the results. Most people correctly identified the ossicles. The cochlear is a little bit that looks a bit like a snail, okay, which is where the liquid is inside, and the stapes are one of the bones. Okay, there's 3 of them in total. Poll 3 is, it's important, and a couple of one or two people on the questions that we answered didn't answer the questions because I don't know, for whatever reason, maybe didn't have a calculator, but we cannot hope to do well in waves if we don't know this equation. It just has to be, that's what it is. Okay, so what does wave speed equal? What is the equation? Okay, I'll end the poll now. Seems that most of you are really quite happy with the with wave speed equals wavelength times frequency. Okay, anything else? Stop sharing that. Any more? A couple more things just to go through. P waves, transverse or longitudinal? P for primary. So they're the first ones. Okay, we're getting up to about the most number of people who've done it. So share results. Most of us got it correct. They are longitudinal waves. Okay, so those of us who were not sure, I've only literally just gone through it, but just make sure that you're aware of that. Stop sharing that one. And the last poll, poll 5, is what medium can't S waves travel through? Okay, so the last question is what medium can't S waves travel through? They provide, this is the evidence for the structure of our Earth. Okay, S waves, the secondary waves that are transverse, cannot travel through. Okay, I'm going to end the poll there, and most of us got it right, is that they cannot travel through liquids, hence the liquid core, the current evidence for that. Okay, did I do that? Okay, then stop sharing, take that off. Right, okay, so I am going to attempt, I'm going to take these slides down because we've gone through all of this. Let me stop the screen sharing. Stop share. I'm going to go extremely large. Now you can see all of that, and I'm going to try now and open up this Q&A. Okay. Do we need to remember the speed of sound in air and water? No, it's good to know it in the speed of sound in air as 330, but not in water. Okay, so that's done for that. Today's topic is essentially what we've looked at. We've looked at ultrasound and seismic waves. I haven't got the revision guide to hand, but there it is in there. Okay. Echolocation, ultrasound works in liquid and air. What about solids? No, that's where it gets, so you know when it hits the seabed and you get that reflection back up, so that's the barrier to it, but it has to be a dense solid, shall we say. So when you're looking at the ultrasound images as we did of the spine of that fetus, we could see that they were you know, they were particularly well lit up there. Isn't the mantle a liquid? Though it's molten. Maybe I misread it. So we talked about the crust that it can definitely go through, and that next liquid layer. Apologies if I said that there being the mantle as that. Yeah, you're right. Maybe I meant the crust going through that. I'll get back to you and see what we did from that. Why are there primary and secondary waves? What causes the different types of wave? It's just the nature of the violent earthquake, also happening in volcanoes as well, but the nature of that, the size of the seismic shift causes two different types of waves to be, it's the phenomenon that happens. Which are the more damaging? It's the primary, because they are the most, the secondary waves are slower. So, you know, you could still have the aftershocks and things like that going from after them, but the initial wave is that. How do you access the recording to rewatch? I'll post it. Okay, I'm never looking at it again. Why does the wave get reflected back after passing through the layer of the pig skin? Because we've got here, what we've got is there's a difference in material, in tissue. Okay, so don't forget, the only reason that this works is because of the nature. Do you remember we talked about how some gets absorbed, some gets transmitted, and because there is the tissue is different, that's how we can work these out. Okay, and then somebody who's put something else in about triple science, can you email me directly, please? Okay, for that one, somebody put a little post at 11:25 from that. Okay, if you have anything else, then please email me direct, or, you know, stick it on the you know, on one of the little classroom things. I've looked and I've got about 3 or 4 questions, exam style questions on this topic, that I'm going to cut into a Google form for those of you who like to do that. I'm going to do that this afternoon for you. So that will be going up on the classroom. And then tomorrow I will do the webinar where we're inviting the higher tier students as well from the combined science, which will be on the electromagnetic waves. So that will also be available for you tomorrow. Now I know where the record button is. If you're not able to make it, I'll load that one up as well. Okay, thanks for coming, everybody. Okay, I'm going to close down this webinar now and let you guys get on and have early lunch maybe. Okay, bye.